Okay, we'll start from here, where we reached the basic idea behind quadratic interpolation, spline interpolation. We are using the quadratic polynomial here as an example. Now we are having different splines, and corresponding to each spline we have different equations, and we have found out that we need three we have three unknowns in one equation, and we have two equations here, and for n splines we'll be having 3n unknowns. And for n splines. So basically we need if you are having two equations here, that means that you will be having if you are having two n splines, you will be having two n equations. You will be having two n equations for n splines, but you will be having 3n unknowns. So this is not possible to find out these coefficients, because we are having a number of equations which is less than the number of unknowns. So we need at least 3n equations. So in order to have these 3n equations, we consider another important fact, that we consider this spline will be having same slope at the interior data points. What that means is that if you are considering this spline, okay, this spline, and it will be continuing like this. But if you take this point, okay, so this is your spline number 1 and this is your spline number 2. Okay, so but this point is common for both these splines. So if you consider the slope at this point, that is dy by dx of that value, and that will be same for this s1 and s2, right, because they are having same points. So what it means that we'll be having ds1 by dx will be equal to ds2 by dx at what point? X equal to x1. This is also at x equal to x1. If you are considering this as at x1. Okay. So at x equal to x1, we will be having these two slopes are same. So that is the idea behind this. So in the first spline we have this equation, that is s1. For s1 we have this equation a1x square plus b1x plus c1, and in second spline we have this equation a2x square plus b2x plus c2, and both at x equal to x1. So this is the general expression. Then if you are calculating the differentiation, then we can have this equation 2a1x plus b1 equal to 2a2x plus b2 at x equal to x1. And then we substitute at this value x equal to x1, then we have this equation, then we have again reduced this equation into this form. So this is the final expression. This one is the final expression, and this final expression is another equation. So we basically have we can also generalize this equation by using the ith and I plus 1 spline. We can write is that expression in general like this. And basically what we are finding out from this is that we'll be having basically we having 3n equations, 2n equation from the previous case, but we discussed from here. We'll be having 3n equations here, because in each spline we have 2 equations. If you are having n splines, then you will be having 2n equations, and after that we are having n minus 1 equation. That is if you are having in this case we are having for example n number of points, let's say. So if you are having n number of points, we will be having n minus 1 number of points which are sharing by if you are having n number of splines, then we will be having n minus 1 interior points which will be sharing. Okay, so this is the basic idea. So if you are having n number of splines, they will be having n minus 1 such points where we'll be having dy by dx or slope which are same, or interior data points which are same for both splines. We'll be having such data points like n minus 1. So we'll be having basically n minus 1 equations. So if you are considering that case, then we have 2n equation previously and n minus 1 equation from this idea of this equalization of the slope at the interior points. Then we will be having total of 3n minus 1 equation now, because 2n plus n becomes 3n minus 1, and this is the total number of equations. Now we apply one more condition, that is the boundary condition. Boundary condition at the, what it means that at the end points we have the second differentiation, or second differential will become equal to 0. That is boundary condition, which is called as natural boundary condition, which means that we have a different number of data points like this, and if you draw the splines between these data points, so it will be like this, and if you take the second derivative of these 2 points at the end points, that will be 0. That is boundary condition. And at the boundary condition, if you apply the boundary condition, then we will be having d square by dx square of xn with, I mean, quadratic equation with xn, that is the last point, and similarly with x0, that is the first point, that's d square by dx square of that spline first one, and last spline. If you take that differentiation equation, then differential second order differential, that will become 0, and you will get a1 equal to 0 or an equal to 0, these 2 conditions. So this you can take any of these condition. So basically what we are considering is that your first or last spline is linear. Instead of quadratic, it will become linear. If you are considering cubic as your fundamental spline, then you will be having a quadratic or a different spline at the end, or the last, or the first one. So that is the basic idea when you are getting n equal to 0, which means that we will be having only bnx plus cn. This is nothing but a line. It is not a quadratic polynomial, it is simply representing a linear function. So that means that we are reducing to linear interpolation, or a spline linear interpolation. So in that case, we will not be having any curve like structure at the end point. We will be having at the end we have a straight line if you are applying this boundary condition. Or you can apply the same in case of the first spline. So in that case, you will be having your first spline as linear, then you will be having quadratic spline thereafter. Okay, so you have to apply the boundary condition. Then now we will be having 3n equation and 3n unknowns. You can choose any of this condition, and you will get one more equation. Then we will be having 3n equation now. We have already 3n minus 1, then 3n equation, then we are also having 3n unknowns. Now equation becomes same as the unknowns, then we can solve this equation easily. Okay, now we will consider another one example and show how we can do these kind of things in the next lecture.